So that means we are going to, again, we suppose that our divisor is of degree k minus 1, or this is equivalent to divisor k minus 1 p infinity. So to be able to obtain a linear code of length q plus 1, that means we need to consider the evaluations of functions at each place. So for the places pi which are different from p infinity, indeed we have similar evaluations. So we have everything works similarly in the previous case. But for the last component, we need to consider the evaluations of the functions at p infinity. And in this case, again, let me consider the basis of the Riemann space L of G. And for up1 up to Pn, Pi's, when Pi's are different from P infinity, we have similar evaluation like in this case. But for the last component, for the evaluations of at P infinity, we need to analyze how these functions behaves for the residue class map O infinity quotient P infinity. Let me denote it by F infinity. Again, also let me write them as V1 up to Vn. V1 alpha 1, Vn alpha n. And indeed, we want to determine how the last component behaves. So here, if we consider the functions u times x to the j, when g is from 0 to k minus 2, so that means until the last component, we can see that by checking their valuations at V infinity, and here recall that principal divisor of u is k minus 1 p infinity minus g, so that means valuations of u at V infinity is going to be k minus 1. And since p infinity is a pole divisor of x, we know that this valuation is going to be minus 1. That means we have k minus j minus 1. And since k is strictly less than k minus 1, because of this condition, we know that this is always positive. So that means this function has always 0 at p infinity. So that means when we evaluate these functions at p infinity, it's going to be 0 of the residue class field. So that means it's going to be 0. 0 of the field FQ. And when we consider the function u x to the k minus 1, so that means for the last component, similarly, we are going to check its valuations at v infinity. So that means v infinity u plus k minus 1 v infinity of x. Similarly, this is going to be minus 1, and v infinity of u is indeed, because of this equality, is going to be k minus 1. So that means this valuation is going to be 0. So that means u times x to the k minus 1 behaves like a constant, constant in this residue class field f infinity. And we can write it like it's gamma maybe it's better to write it. This is from 1 and from 2 x to the k minus 1 u is evaluation at p infinity as gamma, and gamma is a non-zero constant from fq, because p infinity is a rational place and this is a class field is isomorphic to fq. So that means when we extend the length of the Ries-Solomon cos from q minus 1 up to q plus 1, this is going to be the largest case, the longest case. Indeed, we can produce a linear code of length q plus 1 of dimension k, which has specifically has a generator matrix in this form. And in the literature, you may see these codes as extended generalized Solomon cos or simply generalized Solomon cos. So that means for given indistinct points, and given non-zero endpoints, they are not supposed to be distinct. Will be called generalized. Then we can define the generalized Solomon cos, which is denoted by GRS with given k and alpha and v, that consists of all vectors of the form v1 f1 alpha 1 vn f of alpha n with indeed polynomials of degree at most k minus 1. And in their construction, we fix their dimension in the beginning. And obviously, in this definition, if we take alpha as beta up to beta to the n, here beta is a primitive element of the FQ. And if we consider these non-zero vectors as well, we can easily observe that generalized Ritz-Solomon code is nothing but the Ritz-Solomon code we consider in the first lecture. And conversely, okay, we consider a construction by using algebraic function fields, and we observe them as a generalization of the Ritz-Solomon code. And thanks to this observation, indeed, we give the statement, we give the definition of the Ritz-Solomon code by using only considering the polynomials of degree k minus 1. But here we consider the evaluations of the functions from the Riemann-Roch space of the L of G. They are not supposed to be only polynomials. But we can see that indeed any generalized Ritz-Solomon code can be represented like the evaluations in this form, or the image of the evaluation which is described here specifically. So let me fix a notation again. For image evaluation there, so this generalized Ritz-Solomon code, let me use the notation CL, D, and G to denote the divisor G and the rational places PI's and the Riemann-Roch spaces of L of G. And conversely, we can also claim that if we consider the definition of the generalized Ritz-Solomon codes in this way, every generalized Ritz-Solomon code can be also represented in terms of the image of the evaluations of the functions from the Riemann-Roch space of L of G. And similarly, by the definition of the generalized Ritz-Solomon codes, we can consider n distinct places alpha n and non-zero constant vi's, and indeed we can represent these vectors or distinct places by pi's, and let P infinity denote the pole divisor of the transcendental X. So here's the thing, that to be able to choose the function, to be able to write a generalized Ritz-Solomon code in terms of this image of evaluation, we need to see that there should be a function whose evaluations at pi's are equal to this given non-zero vi's. And indeed, we can choose a function whose evaluation at pi is equal to this given non-zero vi's, because this is possible by weak approximation theorem, because by weak approximation theorem, we know that there exists a function u such that their evaluations u minus, of course, they are given also let me state it in this way, for given distinct places pi's and for given constant functions vi's, we know the existence of the function u such that vpi of u minus vi is strictly positive. I mean, you may even describe it by giving their multiplicities in advance. And so that means, indeed, u minus vi, if vpi u minus vi is strictly positive, we know that this difference is a function in pi, and that means u evaluation pi is indeed vi. And indeed, we may even choose this function. We may even choose this function by using the Lagrange interpolation, because here the question is to find a function for given points alpha i's and the outputs vi's. And if we set the divisor as the sum of these rational places, and similarly, if we consider a divisor as a difference of the k minus p infinity minus u, u is the function we choose by the weak approximation, then indeed generalized Riss-Solomon cos is nothing but the evaluation image of the evaluation map we consider here explicitly. So this was a simple case. So we only consider the rational function. We define the Riss-Solomon cos, consider the generalized Solomon cos, and indeed we view them, we describe them by the notions of the algebraic function fields, rational function fields. And the second question, can we extend these definitions, these descriptions for the function fields of genus at least one? And next week we will give the general description and we will investigate what kind of codes do we have when we consider the higher, indeed lower genus 1 or 2 and etc.